Differential equations, type 2, real world. B, power and resistance. In 2012, we had a particle of mass m is fired horizontally through a block of resistive gel. And the resistance to the motion is given by mkv squared newtons when the velocity in meters per second is the speed. We're told the particle enters the gel at a speed of 1,000 meters per second, and 1/100 seconds later exits the gel at a speed of 10 meters per second. So in other words, it passes right through the gel. So the first thing that we have to do is show that K is equal to 99/100. So if we do a little sketch to see what is happening, we have a resistive block of gel, and we have a particle that is going to be fired into the block. So it's moving towards the block, and it has a velocity of v meters per second. But on entering the block is going to cause resistance. In other words, it's going to try and slow that particle down. So we know resistance is an opposing force. And then the particle will emerge. Okay? So if we look at that, then the first thing we want to do is find K. Okay? So once we have a particle entering a block, we're going to have opposing forces. So there is no force going in. We have no kind of tractive force driving it in like an engine or anything like that. It's just a particle being fired in. So therefore the only force we have is the net force, is the resistance. And we're told that the resistance is equal to mkv squared newtons. But of course, because it's in the opposing direction to which the particle is moving, we must give that a negative sign. A bit like retardation or deceleration will have a negative sign. Okay, and that would be equal to ma. So of course then our mass is going to cancel, and that gives us that the acceleration is equal to minus k v squared. So now we have an equation for acceleration. We can look and see, well, what are our limits given to us? What's our start limits and what's our end limits? In other words, what are we going to let A equal? Are we going to let it equal to V dV ds, or are we going to let it equal to dV dt? So of course, we're given our start limits in terms of velocity, which is 1,000 meters per second. And we have the time is 0. We're then told that it exits the gel at a speed of 10 meters per second, and that happens 1/100th of a second later. So our limits are in terms of velocity and time. So we're going to take acceleration as the rate of change of velocity with respect to time. So if I rearrange those, I'm going to get 1/v squared dv is equal to minus k dt. And of course, then that can be written as v to the power of minus 2 dv is equal to minus k dt. And our integral, if we set it up, has the upper limits of 10 and 1/100. So remembering your end limits are your upper limits, and your lower limits then for v is 100, and the lower limit for t is 0. So our start limits are our lower limits. Okay, so let's integrate. With respect to v on the left-hand side, I'll add 1 to the power and divide by the new power. So that becomes v to the power of minus 1 over minus 1 within the limits of 10 and 1,000. And on the right-hand side, if I integrate a constant with respect to t, well, I'm going to get minus kt within the limits of 1/100 and 0. So, of course, v to the minus 1 over minus 1 is just going to be minus 1 over v. So I just tidy that up before I sub in my limits. And then that's going to be minus kt to the power of 1/100 over 0. Okay, so subbing in for v, and then remembering that when you sub in your limits, it's the upper limit minus the lower limit. So that's minus 1 over 10 minus 1 over 1,000 is equal to minus k times 1/100, and of course just minus 0. Okay, so we want to get k on its own, so I'm left with minus 1 over 10 plus 1 over 1,000 is equal to minus k over 100. So if I multiply everything across by 1,000 and then rearrange to get k on its own, well, that gives me minus 100 plus 1 is equal to minus 10k, and of course that's minus 99 is equal to minus 10k, and therefore k is equal to 99 over 10, which is exactly what we were looking for. Okay, so if we're looking at the marks breakdown, we got 5 for setting up our dv/dt, we had 5 for setting up with our limits. And of course you can take out your constant outside the integral sign there if that's your preferred choice. We had 5 for integrating correctly, and we had 5 for getting k. So we actually had quite a lot of marks going there, 20 marks for part 1. So for part 2 then we had to use the fact that dt over 9900t plus 1 is equal to 1 over 9900 natural log of 9900t plus 1 plus c, or otherwise to show the length of the block is equal to 10 over 99 natural log of 100. Okay, so what we want to do basically is set up our integration for the second part of the equation. And of course you can do it with getting c and then working out what c is, or you can use it as normal where we have our limits on either side, which doesn't bring c into account because we're getting our definite integral as opposed to an indefinite integral. Okay, so for part 2, we know that a is equal to minus k over v squared, and if we look at our limits here this time, our start limits and our end limits, well, we have v is equal to 1,000 meters per second, and the displacement is 0. And the end limits, well, v is equal to 10 meters per second, and the displacement is s in terms of meters. Okay, so we're looking for length here. So how far it has travelled just as it emerges the block. Okay, so in other words, it enters the block at a speed of 10, and it leaves the block, it enters at 1,000, I should say. And it leaves the block at 10. So we know the velocity on entering and on leaving, and therefore we could work out the length of the block itself, so the distance that it travels. So therefore, if we're looking at our acceleration, well, with regards to v and s, acceleration can be written as velocity times the rate of change of velocity with respect to distance. And we know that k is minus 99 over 10. So if I rearrange that to get all the v's on the left and all the s's on the right, if I divide v by v squared, I'm going to end up with v over v squared, which is, of course, 1 over v dv. And then I get minus 99 over 10 ds. Okay, so if I now put in my limits, I'm going to have 1 over v dv is equal to minus 99 over 10 ds. And of course you can take your constant outside your integral sign there. And we have our upper limit is 10 and our lower limit is 1,000. Upper limit is s, lower limit is 0. So if I integrate 1 over v with respect to v, we have to spot that on page 26 of our maths tables. Then when I integrate 1 over a linear function, we end up with natural log. So in other words, I have natural log of v within the limits of 10 and 1,000. And if I integrate a constant with respect to s, well, I just get s. So it's the constant times s. And now if I sub in my values, well, I end up with natural log of 10 minus natural log of 1,000. So upper limit minus lower limit is equal to minus 99s over 10. And we want to get s on its own. So if I rearrange that, I'm going to multiply across by minus 1 first of all. So I have 99 over 10 s is equal to natural log of 1,000 minus natural log of 10. And of course then we know from our maths tables, which is page 21, we have our log rules, that when I subtract my logs, so in other words, if I have log x minus log y, well, what do I end up with? I end up with log x over y. So therefore I'm going to have 99 over 10s is equal to natural log of 1,000 over 10, which is of course natural log of 100. And then we just have to finish off by getting s on its own, so multiply across by 10 and divide across by 99, natural log of 100, and of course that's in meters, and that's exactly what they wanted us to show. So for the last part of this question, there was literally only 5 marks going for it. Now again, this could have been a knock-on effect from our project maths era, because obviously integration has changed so much since old course maths to the new maths course, where a lot of integration has gone from it. And they even had to give a hint, if you look in the question that year, to tell you how to integrate. Whereas when you go back to older questions prior to 2012, they wouldn't have had to do that, because we were so used to integrating log functions, especially in applied maths. So I'd imagine that the 5 marks were given that year because it was poorly answered with regards to integration. Whereas normally you have less marks going for finding k and more marks going for the integration. But a nice integration question, and hopefully everybody's happy with integrating log functions at this stage anyway. Okay, so overall 25 marks.